Welcome to DAR Tutors for online and home tuition. Today, we will be covering Chapter 3 of the IB Applications and Interpretation Higher Level Curriculum, Approximations and Error. This topic is fundamental to understanding how we deal with the inevitable uncertainties in the real world when using mathematics. In this video, you will achieve two main learning objectives. First, you will learn to determine the range of possible values for a measurement based on its precision. Second, you will be able to calculate absolute and percentage errors for both individual measurements and results derived from those measurements. By the end of this session, you will be well equipped to tackle IB-style problems involving these concepts. Let's begin. Let's start with a practical scenario to illustrate the core idea. Imagine Abigail measures her height. She uses a tape measure and states that she is 173 centimeters tall. Now, let's think about this measurement. Is it truly possible for her to be exactly a 173,000 with infinite precision? In reality, no measuring device is perfectly accurate. Every measurement has a degree of uncertainty. In this case, Abigail likely rounded her height to the nearest centimeter. This rounding creates a range of possible values for her actual height. Her actual height could be slightly less than 173 centimeters or slightly more. For example, if she was 172.6 centimeters, she would round to 173 centimeters. If she was 173.4 centimeters, she would also round to 173 centimeters. So her true height, which we can call h, must lie somewhere between 172.5 centimeters and 173.5 centimeters. This is the first key concept. All measurements have an inherent range of uncertainty. This idea of uncertainty is crucial in many fields. For instance, if a pilot is 0.1 degrees off course over a long distance, they could end up far from their target. In medicine, measuring a drug dose incorrectly, for example, giving 2 milligrams instead of 2 micrograms, can be life-threatening. Understanding and quantifying these errors is not just academic, it's a critical skill with real-world consequences. Now, let's formalize how we determine this range of uncertainty. We call this errors in measurement. When we use a ruler or any other measuring scale, we are reading off a value between the divisions. If an object's length falls between two marks, we approximate it by rounding to the nearest mark. Let's say a ruler has centimeter marks. If we measure an object as exactly 23 centimeters long, its actual length could be anywhere from 22.5 to 23.5 centimeters. The smallest division is 1 centimeter, and our measurement is accurate to 1/2 of that division. This is a fundamental rule. In general, the precision of a measurement, often called the absolute error or maximum possible error, is half of the smallest unit on the measuring device. So if your measurement was rounded to the nearest d units, the maximum possible error is d divided by 2. This creates an interval around your measured value. The lower bound is the measured value minus this error, and the upper bound is the measured value plus this error. It's important to note that the endpoints of this interval are not included. An actual length could be infinitesimally close to 22.5 centimeters or 23.5 centimeters, but it could never be exactly 22.5 centimeters or 23.5 centimeters if it was rounded to 23 centimeters. If the length was truly 22.5 centimeters, it would be ambiguous whether to round up or down. Similarly, 23.5 centimeters would round up to 24 centimeters using standard rounding rules. Let's work through an example to solidify this. In this example, Ling measures a pencil case and records its length as 18.7 centimeters. Our goal is to find the range of possible values for the actual length, which we'll call L. We have a measurement of 18.7 centimeters. The smallest division this measurement was likely rounded to is 1 decimal place, or 0.1 centimeters. Following our rule, the accuracy is half of this smallest division, so the accuracy is plus or minus 0.05 centimeters. Now we can construct the range. The lower bound is the measured value minus the accuracy, which is 18.7 minus 0.05, giving 18.65 centimeters. The upper bound is the measured value plus the accuracy, which is 18.7 plus 0.05, giving 18.75 centimeters. So, the actual length L lies in the interval between 18.65 centimeters and 18.75 centimeters. Remember, We use strict inequalities here because the endpoints themselves are not considered part of the range for a measurement rounded to 18.7 centimeters. The process is straightforward. Identify the smallest unit of precision, halve it, and add and subtract that value from the measured number to find the interval. Let's apply this to another scenario, this time involving a digital thermometer. Tom's digital thermometer shows his temperature as 36.4 degrees Celsius. What range of values could his actual temperature lie in? We'll follow the exact same steps. The reading is 36.4. The smallest unit of precision is 1 decimal place, or 0.1 degrees Celsius. Therefore, the accuracy of the thermometer is half of that, which is plus or minus 0.05 degrees Celsius. The lower bound is 36.4 minus 0.05, which is 36.35 degrees Celsius. The upper bound is 36.4 plus 0.05, which is 36.45 degrees Celsius. So, we can conclude that Tom's actual temperature T is somewhere between 36.35 degrees and 36.45 degrees Celsius, exclusive of the endpoints. You can see that this method is robust and applies across different units and measuring devices. It provides a structured way to quantify the uncertainty in any given measurement. So far, we've looked at the range for a single measurement. But what happens when we use these uncertain measurements in calculations? Like finding a perimeter or an area. To find the possible range for a calculated value, we need to consider the boundary values of the original measurements. The boundary values are the smallest and largest possible actual values of a measurement. We use these to find the smallest and largest possible results of our calculation, creating a range for the final answer. A key principle here is to manipulate the boundary values to achieve the desired outcome. For example, to find the lowest possible area of a rectangle, you should multiply its lowest possible length by its lowest possible width. To find the lower bound of a product, you multiply the lower bounds of the factors. To find the upper bound, you multiply the upper bounds. This method ensures we capture the entire range of possibilities that could arise from the uncertainty of our initial measurements. Let's apply this principle to a perimeter calculation. We have a rectangular board measured as 78 centimeters by 24 centimeters. We want to find the range of its perimeter. First, we need to find the boundary values for the length and the width. For the length, 78 centimeters, the accuracy is half of the nearest centimeter, which is plus or minus 0.5, so the length can range from 77.5 to 78.5 centimeters. Similarly, for the width of 24 centimeters, the accuracy is also plus or minus 0.5. The width can range from 23.5 to 24.5 centimeters. Now for the perimeter. The formula for the perimeter of a rectangle is 2 times the length plus 2 times the width. To find the lowest possible perimeter, we use the lowest possible length and width. This gives us 2 times 77.5 plus 2 times 23.5, which equals 155 plus 47, for a total of 202 centimeters. This is the lower bound of the perimeter. To find the upper bound, we use the upper limits of the length and width. So 2 times 78.5 plus 2 times 24.5, which equals 157 plus 49, for a total of 206 centimeters. Therefore, the actual perimeter of the rectangular board lies somewhere between 202 and 206 centimeters. You can also express this as 204 plus or minus 2 centimeters, which is the average of the bounds plus or minus half the difference between them. Next, let's tackle a more complex calculation, finding the range of an area. This example involves a paving brick. We measure its length as 18 centimeters and its width as 10 centimeters. We need to find the range of its actual area. First step is, as always, to determine the boundary values for each measurement. For both 18 centimeters and 10 centimeters, the accuracy is plus or minus 0.5 centimeters. So, the length's range is from 17.5 to 18.5 centimeters, and the width's range is from 9.5 to 10.5 centimeters. The area is the product of length and width. To find the lower bound for the area, we multiply the lower bounds of the length and width. So we calculate 17.5 multiplied by 9.5, which gives us 166.25 square centimeters. This is the smallest the area could be. For the upper bound of the area, we multiply the upper bounds of the length and width. This calculation yields 194.25 square centimeters. This is the largest the area could be. Therefore, the actual area of the paving brick lies in the range of 166.25 to 194.25 square centimeters. You can also represent this as 108.25 plus or minus 14 square centimeters by finding the midpoint and half range. Let's work through another problem to reinforce this concept. This one combines a bit of geometry with error analysis. We have a triangular garden whose sides are measured as 8 meters, 12 meters, and 14 meters, all rounded to the nearest meter. We need to find the range of its possible area. The formula for the area of a triangle given its 3 sides is Heron's formula. Area equals the square root of s times s minus a times s minus b times s minus c. Here, a, b, and c are the side lengths, and s is the semi-perimeter, which is half of the total perimeter. First, we establish the boundary values for each side length. Since they're rounded to the nearest meter, the accuracy is plus or minus 0.5 meters. So, side A is between 7.5 and 8.5, side B is between 11.5 and 12.5, and side C is between 13.5 and 15.5 meters. To find the maximum possible area, we need to maximize each term in Heron's formula. This means using the largest possible semi-perimeter and subtracting the smallest possible side lengths. For the minimum area, we do the opposite. The largest possible semi-perimeter is 8.5 plus 12.5 plus 14.5, 2 equals 17.75. Substituting this into the formula with the minimum side lengths gives the maximum area. The smallest possible semi-perimeter is 7.5 plus 1.5 plus 3.5 and 2 equals 16.25. Substituting this with the maximum side lengths gives the minimum area. Calculating these values gives us a maximum area of approximately 46.1 square meters and a minimum area of approximately 39.0 square meters. The IB exam will often ask for the lower or upper bound specifically or the full range. We have now reached the 10-minute mark. Before we continue, I want to invite you to consider expert tuition. If you're finding these concepts challenging or you simply want to achieve the highest possible grades, DART Tutors offers personalized expert tuition for IB, A-Level, and IGCSE. Our tutors are highly experienced and can provide the clarity, tailored practice, and exam strategies you need to succeed. Don't leave your grades to chance. Visit our website or call us today to learn more and book your first session. Now, let's return to the topic and learn how to quantify the badness of an approximation. Now that we've explored the range of possible values, let's learn how to express the error itself in a more direct way. This brings us to the concept of absolute and percentage error. When we measure a quantity, the difference between our measurement and the true actual value is the error. The size or magnitude of this difference is called the absolute error. We can define this mathematically. If V sub E represents the exact or true value, and V sub A represents the approximate or measured value, the absolute error is the absolute value of their difference. The absolute value is used because error is a magnitude, and we don't care if the approximation was too high or too low, just how far off it was. Absolute error is useful, but it doesn't give us context. For example, an absolute error of 1 centimeter is a large error for measuring the length of your finger, but a very small error for measuring the length of a football field. Percentage error provides this crucial context. Percentage error expresses the absolute error as a percentage of the exact value. We calculate it by dividing the absolute error by the exact value, V sub E, and multiplying by 100. This gives a relative measure of accuracy that allows for meaningful comparison, regardless of the size of the quantities involved. Let's apply these definitions with an example. Suppose you estimate a fence's length to be 70 meters, when its true length is set 8.3 meters. Let's find the absolute and percentage error. First, let's identify our approximate value, V sub A, and our exact value, V sub E. The estimate is the approximate value. V sub A equals 70 meters. The true length is the exact value, V sub E equals 78.3 meters. Part A asks for the absolute error. Using our formula, The absolute error is the absolute value of 70 minus 78.3. This is the absolute value of negative 8.3, which is simply 8.3 meters. The absolute error is the difference in magnitude, 8.3 meters. Now for part B, the percentage error. We use the percentage error formula, absolute error divided by the exact value times 100%. This gives us 8.3 divided by 78.3 times 100%, which is approximately 10.6%. This means that your estimate of 70 meters was about 10.6% lower than the true length of the fence. This single percentage number gives us a clear idea of how significant the error is relative to the measurement. Let's work through a more detailed IB-style problem that combines estimation with error analysis. Alan wants to carpet his lounge room, which is 4.2 meters by 5.1 meters. The carpet costs $30 per square meter. He estimates the area by rounding each measurement to the nearest meter. We need to find his estimated area, its cost, the actual area, and the percentage error. Part A asks for Alan's estimated area. He rounds 4.2 to 4 and 5.1 to 5. So his estimated area is 4 times 5, or 20 square meters. Part B asks for the cost based on his estimate. 20 square meters at $39 each gives a total cost of $780. Part C asks for the actual area. The actual area is the true length multiplied by the true width, which is 4.2 times 5.1, equaling 21.42 square meters. Now for Part D, the percentage error in Alan's estimation. Our approximate area is 20, and our exact area is 21.42. The absolute error is 1.42. Plugging this into the formula, we find that the percentage error is approximately 6.63%. This means Alan's estimate was too low by over 6%. Part E asks if Alan will have enough carpet. Since his estimated area, 20 square meters, is less than the actual area, 21.42 square meters, the answer is no, he will not have enough carpet. This example clearly shows that while estimations can be quick, they can lead to significant real-world problems. The lesson here is that when you're dealing with a quantity you need to be sure you have enough of, always round up your measurements to ensure you purchase a sufficient amount. For example, Alan should have rounded 4.2 up to 5 and 5.1 up to 6, giving him an estimated area of 30 square meters. This would have been an overestimate, but it would have guaranteed he had enough carpet. Let's explore another practical application. This problem comes from an ancient Indian text, the Shulba Sutra. The text provides an interesting method for constructing the diagonal of a square. In the process, it offers an estimate for the value of the square root of 2. Part A asks us to show that the diagonal of a square is 2 times the measure of its side. Consider a square with side length S. The diagonal, that D, divides the square into 2 right-angled triangles. By the Pythagorean theorem, the square of the diagonal is the sum of the squares of the 2 sides. So D squared equals S squared plus S squared, which is 2S squared. Taking the square root of both sides, we find that D equals the square root of 2 times S. This confirms the statement. Part B asks us to show that the text's method estimates 2 as the fraction 577 divided by 408. Let the side length as be 1. The text's instructions translate to 1 plus its third, plus this third's fourth, less the 34th part of that fourth. This simplifies to 1 plus 1/3 plus 1/12 minus 1/4. To add these fractions, we find a common denominator, which is 408. This gives us 408 plus 136 plus 34 minus 1 all over 408. The result is 577 divided by 408. Finally, Part C asks for the percentage error of this estimate in scientific notation. First, we find the decimal value of the approximation. 577 divided by 408 is approximately 1.41425686. The exact value of the square root of 2 is approximately 1.4142135562. The absolute error is the difference between these two. The percentage error is the absolute error divided by the exact value, multiplied by 100. Calculating this gives a percentage error of about 0.0015%. In scientific notation, this is 1.5 times 10 to the power of negative 4%. This shows the ancient Indian mathematicians developed an incredibly accurate approximation for an irrational number. We've covered the key concepts. Let's recap what we've learned today. First, we learned that all measurements have an inherent degree of uncertainty. This uncertainty can be quantified. For any measurement rounded to the nearest d units, its actual value lies in the range of the measured value plus or minus d over 2. We use strict inequalities to show that the actual value is not the endpoints. Second, we saw how to propagate this uncertainty into calculated values. By using the boundary values of the measurements, we can find the lower and upper bounds for the calculated result, whether it's a perimeter, area, or volume. Third, we defined and calculated absolute and percentage errors. Absolute error is the magnitude of the difference between an approximate and exact value. Percentage error gives this difference context by expressing it as a fraction of the exact value. It's important to remember that when finding the maximum percentage error for a calculated value, you must test both the lower and upper boundary values of the calculated result against the approximate value. The larger of the two resulting percentage errors is the maximum. Mastering these concepts is essential for success in your IB/AI/HL course, and more importantly, for understanding the world around you. Now, let's move on to some practice questions. Here are 5 practice questions, structured like those you might find in an IB exam. I recommend pausing the video here, attempting them yourself, and then resuming to see the worked solutions. Pause here, work through the problems, and then press play for the solutions. Welcome back. Let's go over the solutions to the practice questions. Question 1 asks for the range of a garden's area. The measurements are 18 by 12 meters. First, we find the boundary values. For 18 mim, the range is 17.5 to 18.5 mi. For 12 niki, the range is 11.5 to 12.5 mi. To find the lower bound of the area, we multiply the lower bounds, 17.5 by 11.5, which is 201.25. For the upper bound, we multiply the upper bounds, 18.5 by 12.5, which is 231.25, so the area is between 200.25 and 231.25 square meters. Question 2 deals with the circle's area. The radius is 4.5 centimeters. This gives a range of 4.45 to 4.55 centimeters. The estimated area is pi times 4.5 squared, which is about 63.62 square centimeters. To find the maximum percentage error, we need the minimum and maximum possible areas. The minimum area, pi times 4.45 squared, is about 62.22. The maximum, pi times 4.55 squared, is about 65.04. The percentage error relative to the minimum area is about 2.25%, and relative to the maximum is about 2.22%. The maximum is 2.25%. Question 3 asks for the percentage error in approximating the square root of 3. The exact value is about 1.732 of 5. The approximate value is 1.73. The absolute error is 0.00205. Dividing by the exact value and multiplying by 100 gives about 0.118%. To two significant figures, this is 0.10%. Question 4 involves the volume of a cube. A side length of 5 centimeters gives a range of 4.5 to 5.5 centimeters. The volume is side cubed. The lower bound for the volume is 4.5 cubed, which is 91.1125 cubic centimeters. The upper bound is 5.5 cubed, which is 166,375 cubic centimeters. Finally, question 5 is a speed, distance, time problem. Distance is 150 kilometers high. Speed is 25 kilometers. First, the estimate for time. 150 divided by 25 is 6 hours. Now, the bounds. The distance is between 149.5 and 150.5. The speed is between 24.95 and 25.05. To find the maximum percentage error, we need the minimum and maximum possible times. Minimum time is min distance divided by max speed, giving about 5.96 hours. Maximum time is max distance divided by min speed, giving about 6.03 hours. The largest percentage error is about 0.6%. Thank you for watching. We hope this video has helped you gain a solid understanding of approximations and error. Remember, the key is to be methodical. Establish the boundary values, calculate the range for the result, and use the appropriate formula for percentage error. If you're looking for more personalized support to ace your IB exams, remember that DAR Tutors offers expert, tailored tuition. Contact us today to see how we can help you achieve your academic goals. We wish you all the best in your studies.